Hey everybody, it's Mr. Spudik back again. Today we are talking about rotation and circular motion. Alright, so let's get going with this right away. Let's talk about a few vocabulary terms that you need to know. First one would be period. Alright, period is the time it takes any object to make one complete revolution. So if you have something that's spinning in a circle, okay, the time it takes for that object to make one full revolution is its period. Okay? We are going to measure period in seconds. And in fact, there's nothing different than the t we use normally. So anytime we have an equation with rotation, we will still have the letter t, and it just means it's still time it takes to make one revolution, but t will always be one revolution, okay, which is period. All right, next thing we need to know is frequency. Frequency will be the inverse, to use a fancy word, of period. Frequency, if you think about it takes so many seconds to make one revolution, well then how many revolutions do you make in 1 second would be frequency. Okay, so the equation is going to be 1 divided by the period. All right, so 1 divided by the period, 1 over t, is frequency. And as you can see, the units for frequency are hertz, Hz. Okay, so you have hertz as Hz, and 1 hertz is actually just 1 over 1 second. Okay, so that is a new set of units, but really, if we look at our equation, we have 1 over t. So if we have 1 over 1 second, okay, so we have 1 over seconds, that's the same thing as hertz, Hz. Okay? All right. So we know period now and we know frequency. Now, frequency, you've seen frequency before, right? Maybe a radio station. You can see the frequency of the radio station. Well, that is still similar to what we're talking about here, even though it's not something spinning around a circle. The frequency, let's say a radio station, DC 101, it has 101.1 megahertz, which means the frequency of the signal is just going back and forth, back and forth, back and forth, 101 million times a second. All right, so we are going to lose and leave the idea of things going in a straight line and think about objects moving in a circle. Okay, now if you remember math class, so if something goes around a circle, the circumference is going to be 2 times pi times radius. So what we're going to do is we're going to take this idea of circumference and kind of fit it into what we've learned so far about velocity. So when things are running around a circle, okay, we will think circumference and we'll remember radius, because radius is going to be important when we're talking about circular motion. All right, so linear velocity. The formula is velocity is d over t, that you remember before. Don't copy that down. Okay, that's old school stuff we've learned a long time ago. Velocity is d over t. So since velocity is d over t, right? But now we need to think in terms of circumference. Instead of a straight line d for displacement, we need to think in terms of circumference. So the equation for linear velocity, which sounds weird, we're saying linear velocity, but it's not going in a straight line. We're saying linear velocity because if I have something spinning around a circle, how fast would it go if all of a sudden it was going in a straight line? Okay, that's a way to think of it. So linear velocity is the velocity we're going to talk about when things are going around a circle, and it's how fast is it really if it was just going to go in a straight line. The formula is going to be 2 pi r over t. And now for some reason in the iPad, some of their symbols do not show up, so there's a pi right there. But linear velocity, v, is equal to 2 pi r over t. Okay? So think about what you have here. 2 is just going to be a constant. We know that from circumference. Pi, we always know that number, and that's something you can easily pull up on your calculator and just type in pi. You could do 3.14, and that will be fairly accurate, but you also remember you always have that pi button in your calculator. Okay? R is going to be the radius of the circle, so whatever's spinning around, that radius of that circle, how far it is from the center of the circle. Not the diameter, but the circle, or the radius. Okay, and t is the period, the time it takes to make one complete revolution. All right, now, if we want to do it in terms of frequency, the formula would be 2 pi r times frequency. So if you needed to jump ahead, let's say you were given a value in terms of frequency in hertz and not in terms of period or seconds, you could go straight to that formula, 2 pi r over t. Alrighty? Okay, now, think about this picture right here. We have, let's say it's 2 tennis balls, and they're attached to one string, but you have a tennis ball on the inner part of the string and a tennis ball on the outer part of the string. And these tennis balls are spinning around. They're attached to the same string, and they're spinning around in a circle as you see that picture. So let's say we're looking down on that, and we see those 2 tennis balls attached to the same string. All right. A couple questions for you. First one would be this. Which ball would have the greater period? Well, they are both attached to the same string, so they would have the same period. All right? Sometimes these are questions on tests, just so you know. I know in my class, I see these questions a lot. So which ball would have the greater period? They both have the same period because they're attached to the same string. They're both going to take the same time to go around in a circle. Okay? The length of the string does not matter. Next question. Which ball would have the greater frequency? Again, they both have the same frequency because frequency is just 1 divided by the period. And if they're both attached to the same string, they both take the same time to go around in a circle. That also means they both do the same number of circles in a set amount of time, so they have the same frequency as well. Final question. Which ball has a greater velocity? The outer ball has a greater velocity because even though they have the same period and frequency, the outer ball has to travel a longer distance in that same amount of time, so we'll have a greater linear velocity. Okay? You could also just think of the formula, right? If we have 2 pi r over t is equal to our linear velocity, and the outer ball has a greater radius, it will have a greater linear velocity. All right, so what's the point for this? All right, I want you to understand that an object with a greater radius is going to have a greater linear velocity. And this can be used for other things around us, okay? This can be used in sports, which I want to talk about. This can be used in other things, all right? The greater radius will give you a greater linear velocity. Okay. So, I have a few questions you could ask yourself. All right? First one talks about a pitcher. His name was Randy Johnson, and he was very, very tall, and he had very, very long arms. So, let's say that I can rotate now my baseball people out there, this is oversimplifying, and I apologize. But, let's say I can rotate my arm just as fast as Randy Johnson, okay? But Randy Johnson's arm is twice as long as mine. Well, then he'd be able to throw the ball twice as fast as me. Okay, now that's oversimplifying other things and other mechanics of pitching, but the greater radius does give you a greater linear velocity. Okay? Catapults, you could apply the same idea to catapults. Okay? Anyone working on cars? All right? Any people that like to get the bigger, fatter tires, you want to get a lift on that truck and get bigger, fatter tires on that truck. Well, if you are going to get bigger tires, all right, and a bigger radius for those tires, well then when those tires rotate, you're going to end up going faster than what your speedometer is telling you. And so that's why if you ever do that, you need to recalibrate your speedometer so that it matches up properly with the actual velocities. Because if you had bigger tires put on your car, think about those tires, the outer edge of those wheels have a greater linear velocity now. So you'd actually have to recalibrate it. All right. Now, tangential velocity. Tangential velocity. You might have heard the word tangent in math class, okay? Sometimes I go off on a tangent on my lectures, okay? Tangent is just meaning going off in a certain direction. Now, when you learn about it with circles, the idea was that you have a line that touches a circle at only one point, okay, and that's the tangent line. The key for that, though, learning from our geometry class, is that that line is always perpendicular to a radius, okay, and that's what's going to be key for us. Let's say you have a ball spinning in a circle right here, okay? If that ball, and obviously this would be that the ball is spinning clockwise, all right? The velocity or the direction of that velocity will always be tangent to the circle, which means that it will always be perpendicular to the circle or to the radius. So if you think about it, let's say this was a ball on a string, right? So if this is actually just a string holding that ball in, that velocity will always be perpendicular no matter which direction that ball is spinning at any point on here, okay? It will always be tangent. Always, always, always perpendicular to the string or tangent to the circle every single time. Okay? All right. So that's just me reminding you that, but the velocity of the ball will always be perpendicular to the string. All right. So I have a question for you. I want you to look at this picture here. All right. So let's say this is me spinning a ball above my head. Okay. So it's flat above my head and you are looking down on top of me right now. Okay. So I have this ball spinning around my head. And again, the ball is spinning clockwise. All right. Let's say that I had a blade and I was going to cut the string at right here at this instant in time. All right, so I'm spinning it really hard. Okay, I really feel a pull. I'm pulling that string really, really hard. Which direction do you think that ball is going to go in? Now I'm going to tell you before you answer. Okay, this is another big concept question, another question that I would give on a test. All right, so do you think it would go in the direction of A, B, or C? The correct answer is that the ball will be going in the direction of C. Because once again, the velocity at that moment in time is going to be tangent to the circle, perpendicular to the radius. And so the velocity of the ball is going in that direction. Okay? And so if the string is cut, it just has inertia. And that was where the velocity was going at that instant in time. And we've learned about inertia before, so all of a sudden there's no outside force acting on it. That ball is going to travel off in the direction of C. Okay? Now, I always ask this question because, and I even emphasize, I tried to trick you, because I started saying that I could feel that pull on the string. A lot of times, people think that the object's going to be getting pushed out, away from the center. Okay? Maybe you thought it was in terms of B, because B was kind of a little bit of it, but yeah, I know about this tangent thing, but there's going to be some pull there too, right? And the answer is no. Okay? There's not going to be anything pushing the ball out. And we're going to talk about that because this is really a huge, huge misconception in circular motion. So much so that you could even get in an argument with your parents about it. And they would think they're right because they've heard this word so much. So, let me backtrack and just understand. So understand tangential velocity. Everything's going to be tangent to the circle. But if we think about this velocity again, remember, at every point in time in that circle, that velocity is changing, right? We just said it's always perpendicular. At every point in time, that velocity is going to be perpendicular. And now that means something. If the direction is always changing, and you've learned from back before or the beginning of the year that velocity is both direction and, or speed and direction. Okay, so direction is important. So if our direction is constantly changing, we have a constant changing velocity. And what do we call something with a constantly changing velocity, or anything that has a changing velocity? What's the A word we use when something has a changing velocity over time? Acceleration. So in this case, anytime a ball is spinning around on a string, because it has a constantly changing velocity, we have a constant acceleration. And we call that acceleration centripetal. Okay, Sir Isaac Newton came up with the word centripetal, and it means center seeking. Okay, so what does that mean? That means whenever we have something spinning in a circle, there will always be acceleration pulling the object in towards the center. Okay, you need to always remember that phrase right there. That's the phrase that pays. Towards the center. Okay, so when I spin something in a circle, I am constantly pulling on that ball. I am pulling that ball in towards the center. Always. Okay, and a lot of people are going to say, oh, well, there's that outside pushing force, right? There's centrifugal force. Okay, there's even a country singer that had that in one of her songs. Drove me nuts. Okay, because there is no such thing as centrifugal. There is no force pushing out. There are only forces pulling in. Okay, and I want you to think about that because people talk about, well, there's if anyone's been at an amusement park or any kind of any fair, you have something that will spin you. Okay, I remember growing up, there's a thing called the gravitron, and the gravitron was this machine where you'd stand against a wall, they'd spin you really fast, and then they'd pull out the floor from you. And they'd say, you'd be like, well, I didn't fall down because they were pushing me back against the wall so much. And that's not true. What's actually happening is you are getting pulled in. Okay? Here's another example to think of it. Let's say that I'm going to ride a jet ski. That would be great. Okay? So I'm going to pretend that I'm riding a jet ski right now. Now, let's say I'm taking that jet ski and I'm all of a sudden going to take a hard right turn. Okay? In a circle. So I'm going straight. And all of a sudden, I'm going to take a hard right turn. So I'm going this way, and I all of a sudden want to go that direction. Am I all of a sudden going to get pushed out to the left? No. It's just that I want to keep going straight. I'm going to have inertia, which we've learned before. My inertia wants me to keep going straight, tangent to the circle. Okay? But I'm going to have the jet ski pull me in. And if the jet ski isn't strong enough, or I don't hold on to the jet ski strong enough, I'm going to keep going straight, perpendicular, okay, tangent. And a lot of people will think there's some type of force pushing you out, but that's not the case. You would continue going forward, okay? Same thing with riding in a car, okay? Hopefully you're always riding in a car, driving safely, you have your seatbelt on. If you don't have your seatbelt on and you take a hard turn, let's say you're driving, you take a hard right turn, it might feel like you're getting pushed out towards a door. Centrifugal force. But that's not a thing. There's no such thing as centrifugal force. What's happening is, as you take that hard turn, you want to keep going straight, and the door is going to keep pulling you in, what's the phrase? Towards the center. Okay? Now, if you have acceleration, you also have force. So I know I would have this question, maybe 2 questions on my test, and I'd say, which one of these arrows is the right arrow for the centripetal force? And which arrow would be the right one for centripetal acceleration? And it's not the arrow down. Don't look at this picture and say, oh, it's always going to be down. No. Okay? It's always going to be the arrow that points towards the center. Okay? So that is centripetal acceleration and centripetal force. And so here's our equation for centripetal acceleration. Centripetal acceleration, I give a little subscript c to point out that it's centripetal, is equal to the velocity squared, which is linear velocity, which we learned before in the previous slides, divided by the radius. Okay? Or if we want to take it a step further, okay, we could also think about force. We already know that force, F equals ma. Right? So if we want to take this acceleration and turn it into centripetal force, all we have to do is put an m in front of it. Like that. Okay? All right, so these are the big concepts. The formulas we have the frequency versus period, period versus frequency. Okay? we have the linear velocity, and then we have a centripetal acceleration, and we have centripetal force. You can put all these together and plug them in to get other equations, and you could really do substitution ahead of time. I'm not going to do any of that on my slides, but you can work on that with your teacher. But understand these concepts: centripetal acceleration, centripetal force, tangential velocity are as important as the formulas as well. That's it for me. Thanks so much for watching.